Okay, thank you. Our second lecture will be about smooth foliations on real manifolds. So now we are not working on a surface of dimension 2. We are working on a manifold M, a real manifold of dimension n. Big O equals n 2. Any manifold, any real manifold of class C1 can be equipped with a real analytic structure which is equivalent to the C1 structure of this manifold. So without loss of generality, I can suppose that my manifold is real analytic. It is not a restriction. Okay? So n can be real analytic if I want. Okay? Now, what is a foliation? So definition. Foliation of class CK, foliation of class CK, K will be at least 1 and less than infinity or real analytic. Okay? The class K of dimension P between 1 and n minus 1 is a family L alpha alpha indices, which will be denoted as L. So is a family of sets L alpha such that first they are disjoint. L alpha intersection with L beta is empty set if alpha is not beta. I forgot to tell that these sets are connected. Connected sets. Second, the union of these sets is a whole manifold. And third condition, most important, is the local structure of these sets. So for every point M in our manifold, there exists a chart. There exists a local chart so local coordinates, neighborhood of point M and diffeomorphism phi from this U to some open set in Rn of class CK. So our manifold can be, well, C infinity, real analytic, but if we speak about foliation of class CK, then chart will be of class CK. So phi will be a diffeomorphism. Okay, U is diffeomorphic under phi to some V in Rn. Yeah? Okay. So there exists a local chart such that the leaves of our foliation in this chart, so intersection of L alpha with U, are mapped by phi to the following set in V. So it's all x in v such that x p plus 1 is constant, and so on, x n is constant. Okay. So locally this set leaf, L alpha is a leaf of our foliation, locally it looks like a piece of Rp. Okay? And therefore every L alpha is a manifold of dimension p, but it is not a submanifold of M because it can be dense in M. It's locally a manifold, but not. Okay, so I started to make a picture. So I'm sorry, I'm very poor artist. So we have manifold, and then I say that for any point I can find a neighborhood. This is a neighborhood, and map this neighborhood by phi to something very regular, to such things. Okay. And so on. So these are leaves here, L alpha intersected with U, and these are images. Phi of U intersect with L alpha. So these are plugs of our foliation. A piece of submanifold T, okay, this is in fact phi minus 1 of T, and T is here. T is a transversalis. This is T, and this is its pre-image, okay? Well, we choose coordinates such that M goes to 0, yes? So here is M, here is 0, and then our T has equation x1 equal to xp equal to 0. So this is a plane orthogonal to these horizontal p planes. Dimension of T is the dimension of T is n minus p, which is called a codimension of our foliation. Okay? Well, so once more, foliation on a real manifold M is a family of linearly connected subsets L alpha which do not intersect with each other. Union is a whole M, and locally they are open sets in Rp. So it's they are all manifolds, but not submanifolds of M. So we had foliation of dimension 1 yesterday on our lecture. A vector field defines a foliation of dimension 1. There is one point. We considered also singular points where this thing is not like that. Today and tomorrow we shall look only for smooth foliations. Smooth means that they are in all points like that. There are no some singularities. Okay? Good. Now I will, okay, this is V. Now look, there is an obvious projection from V to T. There is an obvious projection, pi from V to T to the transversalis. Well, it sends every plug to the point by which this plug intersects T. So in coordinates, it will be P of x1, xp. This will be denoted x prime. X p plus 1, xn. This will be denoted as x2 prime is equal to x prime. This is a map. It's a projection. And of course, you have the same projection here. Everything is diffeomorphic. And starting from now, I shall make no difference between u and v and all this. This is the same. So locally, my foliation is like that, and I have a projection. The triple neighborhood, transversalis, and projection is called a flow box. Flow box of L, of our foliation L. Okay. So this was about foliations. Now I need to speak as little as possible about orientation. In fact, everything I will suppose to be oriented. But nevertheless, I must say few words about that. So if we have a foliation like that, then we have a distribution of planes. Px in the tangent space of a manifold at each point, and Px is tangent to the leaf which passes through point x. And now I'm going to make the following change of notations. So we started from some family of leaves, L alpha, indexed by a set A. But from now, if I want to consider some leaf which passes through point x, I will write Lx. Okay, now if x is different from y, it does not mean that Lx is different from Ly, yes? It can be on the same leaf. But usually, well, it's a custom thing to do. So, at every point, x, you take a tangent plane to the leaf at this point. Okay, so this is a subspace of dimension p in the tangent space. It varies smoothly depends on x, and foliation is called orientable if these planes, subspaces can be continuously oriented on M. What does that mean? That means that locally you can find vector fields. What was my notation? Better to keep notation. Okay. Locally you can find vector fields V1, Vp, generating P. Okay, not very good. This will be Greek P. Okay. Generating is a basis of P at point x. And so you can find, and this defines you a orientation. It's a base of Px, so it's defined orientation. And then if you are in a neighborhood of this point, this orientation is continuous. So you can cover manifold by open sets okay, foliated charts, flow box, whatever you want. And in each open UI, you can find such vector fields. They are smooth, of course, smoothly dependent on x, such that at every point, this will be the corresponding tangent to the leaf. So if you can do that, if you can orient continuously the leaves of your foliation, you say that foliation is orientable. So we had this question yesterday with foliations of dimension 1. What does it mean to orient foliation of dimension 1? It means that to find a vector field which is everywhere tangent to the leaves, okay? And we proved, or no, we not proved, I said this is the exercise, that on the simply connected manifold, if you can locally orient your foliations, then you can find this vector field globally. Okay, and that's it. I'm not going to go further. I want to say the following thing. This is orientable foliation. And another point which I need to say is what it is a transversally orientable foliation. Well, for every tangent space, well, you can find another subspace of the tangent space such that which is complementing to P. Okay? So if you can you find subspace which is orthogonal with respect to some Riemann matrix, is not a problem. But the point is that if you can orient this distribution continuously, then you say that your foliation is transversally orientable. Okay? Now, we can forget about that because all significant results of today will be for manifold which is simply connected. Simply connected manifold is orientable itself. Any foliation on the simply connected manifold is orientable and transversally orientable. This is discussed a little bit in my notes, but mostly as exercises. Okay, but I don't need to stop on that. And that's all about orientation. And now the third point is more important, is transverse curves. Okay. So from now on, our foliation will be of codimension 1. L is a smooth foliation on M, and codimension of L is 1. So if dimension of M is n, so the dimension of leaves is n minus 1. Okay, codimension 1. So foliation locally by hypersurfaces. Now look, if you see all this for the first time, then I suggest you to think about R3. So M is R3, and you have foliation by surfaces in R3, at least locally. Globally, it can be very complicated, but this is something you can think, you can have in your mind. So the main theorem, which will be proved tomorrow, will concern the case of foliations on manifolds of dimension 3. Okay, but not today. Today it will be any dimension. And lemma 1, everything orientable. Everything is orientable. And now lemma 1, there exists a transverse curve gamma from S1 to M transverse to L, to the foliation. Well, that's clear what I mean, yeah? Curve which is everywhere transverse to the leaves. This is the first point. If L0 is a compact leaf, of our foliation, if such leaf exists, and if gamma of S1 intersects this leaf, is not empty, then there exists another transverse curve. There exists a transverse curve V gamma tilde such that it intersects L just by one point, only once. So we have a manifold, we have a foliation. By the way, it is not important that it is orientable, but okay, everything is orientable. Then we always can find a closed transverse curve. And if we have a transverse curve which intersects a compact leaf, better to say if you have a compact leaf. It's not obvious if you have a compact leaf. But if you have a compact leaf, then of course we can arrange that transverse curves intersect this compact leaf. It's not a problem, you will see. But then what we can do is make that this curve will intersect this compact leaf only once. Okay, proof. Oh my God.
So I can use this, I think that I cannot.
Yeah, it will work for 5 minutes. Okay, okay. No, you just say me, and then I shall look for another pencil.
It's L0.
What?
S1 intersect L0.
L0, yes, thank you. A proof. So our foliation is transversely orientable, yes. Therefore, we can find a transverse vector field. Okay. Now, if it's not orientable, then you can prove that you can pass to double cover of our manifold and make this orientable. So it's not important at all. Okay, so we can find a transverse vector field, and then we can solve an ordinary differential equation and find a, well, manifold is compact. Okay. And we can find a trajectory, gamma from R to our manifold, such that gamma point is V of gamma of t for all t. So we can find a trajectory, meaning a curve which is tangent to this vector field at every point. Now it has omega limit set. Well, it's a closed subset, not empty of M. And we can take a point on this omega limit set. So a point such that in any neighborhood our curve intersect many times this neighborhood. Okay, so let us make this picture. This is our point P. Okay, so on this picture we have dimension 2, foliation dimension 1. And now we have the following thing. Our curve passes somehow close to P, but then it passes once more somewhere. So in this direction, and then it passes, because orientation is preserved, so it passes once more somewhere here, another time in the same direction. And you can do this thing. You can close this curve. Okay? This, and this. So you can erase this, and this curve will be a closed curve. Okay, so it's very simple. So this was the first point. Second point, you have a compact leaf, L0. And now you have a transverse curve which intersects L0, and suppose that more than by 1 point. But then you can do the same. You take this picture and you deform your curve this way. And now you have 1 point less. You decrease the number of points of intersection. And you can do this until you have 2 points. If you have 1 point, then you are finished. Okay? So this was first lemma. Yeah?
So, I mean, to be able to do this, do you need, in the intersection, do you need finitely many points?
But this I have always. Now look, my curve is closed. Well, okay.
The compactness of the leaf.
But I need compactness of the leaf.
Yes.
Okay. Okay. Now the next thing is a so this I shall keep. Now we shall need a Morse type lemma. Okay, so let me recall you that if you have a smooth function f, smooth of class C2 at least, on a manifold D, and suppose you have a point such that gradient of f at P is 0, a critical point, then you can find local coordinates near P. You can find y1, 1, m is the dimension of D. Local coordinates near P such that, well, P in these coordinates is 0, and your function f of y is minus y1 square minus yk square plus yk plus 1 square, etc., plus ym square. The number k is called index of f at P, or index of the critical point P, if you like. Okay, this is a Morse lemma. And now, what happens in dimension 2? I will need dimension 2. So D, let be a unit disk in R2. So what are possibilities? So you have three possibilities. First is your function has both positive. The second possibility, your function has index 2, is here is index 0, okay, somehow more or less the same. And the third possibility is that your function has 0 as a saddle point. Okay, on the picture, what are level sets? So this means, well, what are, in the first two cases, level sets are like this, circles around 0. And 0 is a focus. Be careful of the focus. Okay, now in this case is a local minima, in this case is local maximum. Okay, and in the third case, it's a saddle point. So the level sets are like that. So you have a saddle. Okay, and now I will need lemma 2. Let L M be as above. So L is a foliation on a compact manifold of codimension 1. Okay. Codimension of L is 1. Smooth of class CK, K at least 2. Okay. Let F be a smooth map from the closed unit disk to M. Be a smooth map. Well, CK, of class CK, of course, be a smooth map. Then F can be approximated or perturbed in a CK topology, so smoothly approximated, by map G in general position. So this map G will be called map in general position, and that means the following. First, the image of the circle, so this is the curve, is transverse to L. Second, for any flow box U T P, if you take a composition of projection P with G, where it is defined, okay, it's defined on some. If a flow box intersects the image, so it's somewhere defined, is Morse. Well, and the third condition is if P1, P, what was it, L, are points of tangency of G of D with L, So points where this guy is tangent to leaves. You cannot avoid this in general. How you perturb your map, you may still have some tangent points. So the claim that you can do such in such a way that you will have only finitely many tangent points, well, that's almost obvious. But more important is that then for pi different from pj, for two distinct points, they are on different leaves. Leaf L pi is different from the leaf L pj. Okay, so let me try to make some, well, so you have, no, I cannot, I'm sorry. So, but I can do some local thing. So if this is a leaf, and then your disk is somehow tangent to this leaf at this point, then we say that projection is Morse. And what are the level sets of projection? Level sets of projection is curves which are intersections of this leaf, of leaves with this disk. So now it is Morse, so there is two possibilities. And one is that intersection is like that. So the foliation induced on this disk, our foliation intersects this disk, and it induces on this disk a dimension 1 foliation. So it has a singularity focus, but may be also, now I will try to depass my possibilities. You might intersect another leaf, and this I'm not able to draw, but something by a saddle. Okay? Don't ask me to draw this. And then you can have a saddle point. So the leaves will be like that. And no other singularities, only focuses and saddle points. And two singularities cannot be on the same leaf, and that means the two singularities are not joined by a trajectory. So if F is a foliation induced by L on our disk, you write this as J star of L, or you can write this as disk intersected with L. I think it's clear what I mean. So this foliation has this particularity. In a moment, I shall prove that this foliation is orientable. It's well, a little bit later. But it has singular points, only focuses and saddles. And no two singular points, there is no, well, no trajectory can go to focus, but you might have two saddles. Okay? But there is no trajectory which goes from one saddle to another, because these are on different leaves. And this is the first thing. And this foliation induced on this disk is orientable. Why? Because locally leaves are projections, composition of P composed with J. Well, denote this as H, for example, locally, in the neighborhood of any point. Some point goes to some flow box. In this flow box, you do that. And level set of H is your foliation. But then you can consider a gradient of H. So dH over dy, dH over dy2 And this, as we know, will be orthogonal to the level sets of H, yes? And then you can take vector field, which is orthogonal to this, minus dH over dy2, dH over dy1. And so this field will locally orient your foliation. So it will be 0 at critical points, and otherwise it will be tangent to the leaves. Okay, that's fine. So our foliation is orientable, and we can apply Poincar-Bendixson theory to this foliation. Okay, now I'm not going to prove this lemma. Well, just general position lemma you can find in my lecture notes, detailed proof of this. Okay, this was lemma 2. And now,
Pardon, by saying that the function is Morse, you mean that it's one of these two?
yes. It's of this kind. That's why I discuss it here. Okay. So level sets are very nice.
And on the third part, the number of tangency is finite also?
Yes.
By compacity?
Not by complexity, by general position. If everything is real analytic, then it's fine. But if smooth, then you can have some smooth foliation, you can arrange some disk which is tangent along a curve, I don't know what. But if you perturb, you can make it finite, yes. And moreover, you can make it in this way. Now, this was the following thing. And now I need one more lemma, and then I can prove the theorem. Okay, now, about this foliation, induced foliation. So I have a disk, and I have a foliation F on the disk, which induced by L and by mapping J, which I have. I know that this foliation is orientable, and it is transverse to the boundary. So it's like that. Along the boundary, it's nothing else. And I know that there is a vector field, which is directed along the leaves. If it had happened so that vector field looks out, then I take minus V. And I will get a vector field which is tangent to the leaves of this foliation, but which is pointing to D. So I am in the Poincar-Bendixson setting, and I consider the set of C, set of polycycles of this vector field. Okay, recall that a polycycle is a... Now, in our case, it's a very special thing because two saddles cannot be joined by a trajectory. So in this case, we have only following possibilities. It can be a cycle, a smooth trajectory. It can have only one saddle. Cannot have two saddles, and so it can be like that. Like that, or it can be number 8, and there is one more possibility, it can be like that. And no other possibilities. That's all you can have because of these conditions. Okay, so we have only saddles, nice saddles, focuses we have, and no two saddles can be joined by a trajectory. So these are our polycycles in question. So we don't have others. And we denote by B. So if gamma is a polycycle, we denote by B gamma the closure of the open set which is bounded by gamma. It might be not connected. Look. Here gamma bounds two distinct open sets, not intersect. We take a closure. Okay? And now we say that gamma 1 is smaller or equal than gamma 2 if B of gamma 1 is a subset of B of gamma 2. So we have a partial order on the set of the polycycles. And lemma 3 is the following. Let gamma n be a decreasing sequence of polycycles. Let B infinity be intersection of all B gamma n, and define gamma infinity as a boundary of the B infinity. Boundary is the usual sense, okay, boundary of the set. Then gamma infinity is a polycycle. So intersection of a decreasing family, of a decreasing sequence of polycycles can be only a polycycle. It's, well, on the first glance, this is almost obvious because you have some singular points here and you have very few possibilities to make a polycycle. But in fact, it's not as easy, and proof is again given in my lecture notes. Okay? And now, the proof of this thing is based on the Poincar-Bendixson stuff entirely, and it uses in the crucial way the monotonicity lemma. So it repeats more or less the proof of the Poincar-Bendixson. Okay, and now I'm going to state and maybe prove the second theorem of my course. So, theorem of Haefliger. A compact simply connected. This is important. A compact simply connected. A real analytic manifold. Real analytic manifold. Does not admit a real analytic foliation, or a codimension 1 a real analytic foliation. So for example, sphere in any dimension, okay, does not admit a real analytic foliation of codimension 1. Okay. Now, what is the proof? Well, suppose it does. Suppose it does. So now, so we have a foliation on M. We can construct a transverse curve which is transverse, okay, by lemma 1. since M is supposed to be simply connected, this curve is homotopic to 0, and that means that there exists a map from the disk to M such that on the boundary this is our curve. And now we can approximate, we can perturb this map to have, we can get J from here, having these properties. In addition, we can make J to be a real analytic. So why? Any smooth map by Weierstrass theorem can be approximated by polynomials, and therefore every smooth map with values in some manifold can be approximated by real analytic maps in CK topology. And now you can observe that any map which is C2 close to the generic one will be generic one, will be in general position. So this is generic thing. Okay. So we construct real analytic guy which has these properties. And now we can apply all this stuff. Okay, so now we consider C bar, the set of all polycycles which are all polycycles of course this foliation we have on D, which are either limit polycycles, either a limit polycycle, limit polycycle means that something approaches them in the limit, like in Poincar Bendixson theorem. It's not a periodic orbit, it's just a limit. And second, polycycles which appear as in lemma 3. Well, roughly infinite intersections of limit polycycles. Note that polycycle which appeared in this way may not be limit polycycle itself. For example, it can be like that with your gamma infinity. And then you have some polycycles gamma n which approach, and each is a limit. So for each you can construct a curve which is close to it, and so on. But you will not have a curve which is approaching to gamma infinity. Okay. So we consider all this set. So, and a point, the lemma 4. I'm afraid that I'm arriving to the end. Lemma 4. Now we have a partial order on this set, like here. And claim is that there exists a minimal element of C bar. Okay, well, this is a combination of this statement that you have a family of compacts such that each finite sum family intersects, then they intersect, Thorn lemma, and some Poincar Bendixson stuff considerations. So it's not very difficult. Well, it is proved in my notes. And now, so it contains a minimal element. Let gamma be this element, this polycycle. So minimal, that means, very simply, that it does not contain any other polycycles from C bar. So which are either limit polycycles, either intersections of limit polycycles. So let gamma be this polycycle. Okay, there are two possibilities. Either this is an orbit, or it is a number 8. So what is that? Oh my God. Okay. And now, proof is the same in both cases. Let me look here. Take a transversalis. Then you have Poincar first return map, which we discussed. What is that? You take a point on the transversalis. You take a trajectory, and it goes and intersects transversalis for the first time. This will define you a map H from T, let's do point P, in a neighborhood of P, to itself. Now let us remark first thing that B is a, so it is our gamma, B is a open set bounded by gamma. So first thing is that this map, if you restrict it to the part of transversalis which is in B on this interval, this is identity. So why is that? If not, if it's not identity, then you have something like that. Okay? So if you have something like that, that by Poincaré-Bendixson, it will accumulate either to a polycycle, which is forbidden because this is a minimal one, or a saddle point. Well, let's suppose it accumulates to a saddle point. Okay. But then remark that you have only finitely many saddle points inside. Okay, because every saddle point is an isolated point in its neighborhood. Okay, but you have infinitely many points on this transversalis. So you can find S such that it will not accumulate to the saddle point. It will accumulate to a polycycle, which is impossible. So the only possibility left is that this trajectory is periodic. It's like that. It starts at S and it ends at S. No other possibilities. And so this map is identity. And second remark is that if you restrict this map from this side on T intersection of D minus B, so here it was identity. And now if I restrict it here on this part, then it is not identity. Why is that? Because our gamma is either a limiting cycle or is approximated by limiting cycles. What does it mean? That very close to gamma you can find a cycle which is a limiting cycle, and that's why the first return map cannot be an identity. So if you have another, maybe gamma itself, or another which is close to gamma and which is a limiting thing, then it means that some trajectory is doing like that, accumulating to this closely. And so your Poincaré map cannot be identity. So remark that this we proved, and this is valid always. So we proved some positive thing, that if you have a codimension bound foliation on simply connected compact manifold, then we can find a disk, and we can find the embedded disk, and we can find a cycle which has this property. But now, if our foliation was real analytic, and if this guy was real analytic, then the Poincar map is also real analytic. And this is impossible. It contradicts to the identity theorem. Okay? So real analytic such thing cannot exist. Now, well, is this finished?
Yeah.
Yeah.